Welcome to part 3 of wave motions. And we are now talking about baroclinic instability. And straight from the glossary of meteorology, here's the definition of baroclinic instability. It's a hydrodynamic instability arising from the existence of a meridional temperature gradient and hence vertical shear of the mean flow and a thermal wind in an atmosphere in quasi-geostrophic equilibrium and possessing static stability. What the hell does that mean? That's pretty complicated. You probably have seen some of those words before, like thermal wind and vertical shear and temperature gradient. But what you can think of as baroclinic instability is basically the process that makes weather systems go. We're talking, low pressure systems that move across the United States and northern hemisphere, also southern hemisphere, that has warm fronts, cold fronts. They eventually occlude. So we're going to look at what's driving baroclinic instability. And you can relate it to the energy that a system has. Usually a system starts out with high potential energy, converts that potential energy to kinetic energy, and pretty soon all the potential energy is turned into kinetic, and then eventually the kinetic dissipates also. So our initial condition, you have high potential energy. It's like a ball above the ground. It's at a high altitude and gravity is pulling it down. You let the ball drop and that potential energy is converted to kinetic energy. And in that process, it's losing potential but gaining kinetic. That's what's happening in our atmosphere. If we look at a cross-section from the North Pole down to the equator, more or less you've got a strong temperature gradient from north to south. Up north it's cold, down south it's warm. So this is a situation where you have high potential energy and not a lot of kinetic energy. It's not moving yet. The system's not moving yet. If we remove the divider in between these two masses of air, then you're going to see the air start to flow. The cold air is going to undercut the warm air. The warm air is going to rise and move up over the cold air. So you have your potential energy being converted to kinetic energy. Eventually, over a period of time, what happens is all the warm air rises and all the cold air sinks. Warm air stays up high, cold air stays down low. Your kinetic energy is starting to dissipate, and you have not much potential energy either. You don't have a lot of energy to tap to make the wind move or make the air move. So you've had conversion from potential to kinetic, and then the kinetic energy dissipates by viscosity and also by friction. So this is what happens in the atmosphere, and this is what is baroclinic instability. You start out with a stationary front. Pretty soon winds start flowing around that front. If there's a little disturbance, a low develops. That low intensifies, the winds move faster with this temperature gradient. Cold air is coming down to the south, warm air is moving up to the north. Pretty soon that system cuts off and occludes, where all the warm air is pushed high and all the cold air is down low. You've got you've got good kinetic energy, but the potential energy is gone. And pretty soon the kinetic energy disappears by friction and also viscosity. It just spins down. So that's what's happening in our atmosphere. Without any equations, I know that's a first, but that's what happens with baroclinic instability. You start out with a temperature gradient from south to north. This is looking at like an 850 millibar map, looking at contours, lines of constant height, and also isotherms. This is an equivalent barotropic situation. And if you did a cross-section, down south you would see pressure surfaces that are farther apart, and up north, pressure surfaces are closer together because of the cold air. If you look east to west, you're not going to see really big slopes in the pressure surfaces because you're looking at pretty much all the same temperature at this point as you go from east to west. Oh, there's our first equation, the thermal wind. So because we have a horizontal temperature gradient in a layer, we are going to have a thermal wind, which means the wind increases with height. So you do have a jet stream, but you don't have a jet streak yet because you don't have any regions where the temperature gradient has been enhanced. And lo and behold, a long wave moves over this temperature gradient and disturbs it. You can see that there is a little bit of curvature, and with that curvature, that's going to imply some cross-contour flow and some rising and sinking motions as a result of the vorticity equation. So pretty soon you get convergence on one side and divergence on the other. Convergence causes sinking motion because this is convergence aloft. Divergence is going to cause rising motions. So you start to see rising and sinking motions in the atmosphere. When that happens, that's going to intensify the surface highs and the surface lows. You're going to see surface divergence with that high, and you're going to see surface convergence with that low down low. And as a result, you're going to see these systems intensify. So as they intensify, the pressure gradient at the surface gets stronger and the circulation around these systems gets stronger. So the low starts pulling down cold air from the north and pushing warm air up towards the north. With that, you've got temperature advection. Advection causes regions where the temperature gradient is a little bit stronger, which induces a jet streak aloft. With the jet streak, you start to get more circulations, more rising and sinking motions associated with the jet streak, and as a result, you'll get frontogenesis. So this is what your east-west cross-section looked like before we had all that temperature advection. Now to the west, the cold air is coming down. To the east, warm air is moving up. And pretty soon, this is what it looks like. With that cold air, the thicknesses are less. With the warm air advection, thicknesses are greater. So you'll start to see this trough tilt to the west, and it looks something like that. This is what you see with young weather systems that still have a strong temperature gradient and also strong temperature advection. So this is what's happening. You've got this upper level trough that sits behind the lower level weather system or the low pressure system at the surface. So the upper level low or the surface low precedes or is farther to the east than the upper level trough. So as this weather system intensifies, the baroclinicity of the system also intensifies, meaning that the temperature gradient gets stronger as a result of the temperature advection. And with strong temperature advection down low, you're going to see those thicknesses change. And this is what actually happens. You can see this on the weather map. This is this is a 500 millibar map, and you can see the trough and how it intensifies later on with cold air advection and those heights fall. So with that strong temperature gradient, you get a jet streak as a result of the thermal wind. And that causes these secondary circulations in the exit and entrance region. You remember your thermally direct and thermally indirect circulations, which intensify the surface low and the surface high. And towards the older stages or later stages of this low pressure system's life cycle, that cold air that came spilling down from the north eventually spills to the south and starts to spill back up to the north. In other words, it circles that low pressure system. When that happens, that warm pool of air starts to become just a sliver. And that's where you start to lose the potential energy of the system. In other words, this weather system needs that temperature gradient to make it go. Once that temperature gradient disappears, once all the warm air is pushed aloft, and down low you have all cold air, all the potential energy has been wrung out of the system. You still have some kinetic energy, but you don't have anything else to make it go. And that's what happens. The warm air rises, the cold air sinks. Over a period of time, what happens to the kinetic energy is that it loses kinetic energy through viscosity. In other words, the stickiness of the molecules, the friction of the air against itself, and then also the friction of the air as it blows over the ground. So this weather system spins down. It doesn't have any more energy, potential energy to tap to make it go. And this is what happens. It occludes. The cold air wraps around the low, and a new low develops to the south, where you still might have some temperature gradient. And it becomes an old weather system. We talked about these. It's a cold core low. In other words, all the cold air is in the center and the warm air is around the sides, way away from the weather system. And you don't have any energy anymore to make it go. So it just sits there and spins. And only that, the jet stream ignores that low pressure system, the old low, because the jet stream follows the temperature gradient. If there's no more temperature gradient around that low, if it's cold around that entire low, it finds a new path, and it follows the new temperature gradient, the stronger one, to the south, and it ignores the old low. So that's baroclinic instability and how weather systems move.